There is one more crazy thing that we need to know about electrons, and that is that they interact with a magnetic field. So if we put a magnet here and we run a beam of electrons through it, they interact with a magnetic field as though they have a magnetic property themselves, so that some electrons are attracted towards deflected upward from that magnetic field, and some electrons are deflected down. So some electrons behave as though they have a north pole magnetic field, and the others behave as though they have a south pole magnetic field. This property of electrons we call spin, because it's sort of similar to a charge that's spinning would have a magnetic field with it. And if the electron were spinning clockwise, it would have a magnetic field that would be oriented differently than if it were spinning counterclockwise. The thing to understand is that electrons don't actually spin. They have an intrinsic magnetic moment, and they interact differently in a magnetic field depending on whether that magnetic moment is pointing up or pointing down. So we do talk about electrons as though they have spin up, and when we have an electron that's spin up, we draw a half arrow up, and electrons that are spin down, we draw a half arrow down. So we call this spin up, and we call this spin down. And so we give these electrons another quantum number, because they can only be spin up or spin down. That's the only two directions that they can be. And so if it is spin up, then we say the magnetic spin quantum number, or m sub s, is equal to a half. And if it's spin down, the magnetic spin quantum number is equal to minus a half. And so there's a fourth quantum number with each electron, and that has to do with its magnetic moment, whether it behaves like a spin up or a spin down electron. The reason this spin concept is important is because electrons behave in such a way that within an atom, no two electrons can have the same set of quantum numbers. So we call that the Pauli exclusion principle. And what it says is that each electron in the atom must have a unique set of quantum numbers. So if we have two electrons that are both in a 1s orbital, so let's say they're in the 1s orbital. So that means that their n quantum number is 1, their L quantum number is 0, and their m sub L quantum number is 0. So this is n, L, m sub L. So I can put one electron as a plus 1/2 m sub s quantum number, spin up, and I can put another electron in the exact same n, L, and m sub L, but as long as I make its m sub s quantum number different, so I put it spin down, those will be different quantum numbers, and that will be allowed. That is perfectly acceptable. So that means that in each orbital, I can put two electrons, because I can put one spin up and one spin down and still have all of them, both of them, having a unique set of quantum numbers. Thus, when I am thinking about where the electrons are in a particular atom, I'm always going to put two electrons in each orbital. So using this idea, if we want to write out or decide where the lowest possible energy for the atom would be, we're going to put each electron in the lowest possible orbital, the lowest energy orbital that we can put it in. So helium has two electrons, and I can put one spin up in the 1s, and then I can put one spin down in the 1s, and that's the best I can do for helium with its two electrons. Both of those are in the lowest possible orbital, and so that's going to be the lowest energy configuration for helium. Lithium has 3 electrons, and so I would put one spin up in 1s, one spin down, but then the next one can't go in 1s. It can't be in the lowest one because I've filled up that orbital. I can only put 2 electrons in each one, so it's going to have to go in the 2s. I can either write that spin up or spin down, doesn't really matter. I usually start with spin up. And then let's move on to boron. So let's skip beryllium. Let's do boron. Boron has 5 electrons. And so I have to put 5 electrons in here. So I'm going to do, start in the lowest, put 2 in each. 1, 2, spin up, spin down. 3, 4, spin up, spin down. Now I need to put 1 more. And so that can go in the 2p because that's going to be the next lowest energy level. Notice that I've drawn 3 lines for the 2p because remember that the 2p orbital, L equals 1, has the possibility of m sub L being -1, 0, and 1. So there are 3 of those that have exactly the same energy. But they're 3 separate orbitals, and so they can each contain 2 electrons. So for the p levels, I have 3 separate orbitals, all of the same energy. So let's move on to nitrogen because that illustrates a different principle. So nitrogen has 7 electrons. So we're going to go 1, 2, 3, 4, 5, 6, 7. But where are we going to put those other 2? So it turns out that it's lower energy to keep them with the same spin in different orbitals if I have orbitals of the same energy. So remember, these 2p orbitals are all of the same energy. So if I can spread the electrons out in those 2p orbitals, they won't have to get as close to each other because remember those 3p orbitals are oriented differently in space, so they don't get as close to each other, so there's less repulsion. Less repulsion means that the energy isn't raised as high, so it's a lower energy. Remember, repulsive energies raise the energy of the system, so we want to reduce the amount of repulsion. So if I can put them in separate orbitals, that's better than putting them in the same orbital, as long as the orbitals have the same energy. So as long as they're what we call degenerate. So that's a good word to remember. So orbitals with the same energy, the 2p orbitals, for instance, are all degenerate. That's the word we use to say that they have the same energy. So if the orbitals are degenerate, if they have the same energy, then you want to put the electrons in separate orbitals first before you begin to pair them up. And it turns out that they're lower energy if they all have the same spin, either all up or all down. And that is called Hund's rule. So the fact that we separate these and have them all the same spin is called Hund's rule. So using this idea, we can write what we call the ground state electron configurations of each of these atoms. Ground state, meaning the lowest energy, electron configuration of each of these atoms. So how I do that, I shorthand it by saying that helium has 1s, 2. So I use a superscript 2 because there are 2 electrons in the 1s. So that means for lithium, I would write 1s2, 2s1. And I can leave the 1 off if I want. If there's no superscript, we just assume that it's a 1. But for completeness sake, let's put the 1 there. And then boron would have 1s, 1s2, 2s2, 2p1. So notice that all I'm doing is taking the subshell that the electrons are in, how many electrons are in that subshell as a superscript, 2s has 2, 2p has 1. So when I get to nitrogen, it's going to be 1s2, 2s2, 2p3. So what I do is all of the 2p's, I count up all the 2p's no matter which of these lines they're inhabiting, and I use the superscript for the total number of electrons in that 2p level, because remember, they're all the same energy level. So that's what we call, this is what we call electron configurations. And we've written the ground state electron configuration because we've written the lowest possible energy configuration for each of those atoms. So you should be able to write the ground state electron configuration for any atom that I give you in the periodic table. So let's just randomly pick an atom. So let's do iron, for instance. Okay, so if I'm going to write the electron configuration for iron, I'm going to do it this way. I'm going to look at the periodic table and I'm going to say, well, it has 26 electrons. So it has all the same electrons as all the elements up until iron, and then one more, the one that iron, the 26th electron, right? And so I know that the first row is filled, right? So I have 2 electrons in the 1s. The second row is filled, so the 2s and the 2p's are filled. The 2p can take 2 in the first one, 2 in the next one, and 2 in the next one, so it can take a total of 6, right? Because there's 3 levels, 2 electrons in each. So 2s2, 2p6. And then I can see that I need to fill the third row, and the third row has 3s2, 3p6. So 3s2, 3p6. And then I need to go to the fourth row. And in the fourth row, I've got 4s, but then these guys start to fill the 3d. Remember, this is n minus 1d that gets filled here. So I've got 4s2 and then 3d. 1, 2, 3, 4, 5, 6. 6. So that would be iron's ground state electron configuration. You can do that for any atom in the periodic table if you understand how the periodic table is put together in terms of N shells, S, P block, D block, F block. Okay? So once we have that ground state electron configuration, we can write it like this, or sometimes you'll see it with all the 3 shell together and the 4s out here. So an equally good way to write this would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, 4s2. So you'll see both of those possibilities. Either one is fine with me. Okay, so that's a lot to write down. We can do a shortcut. So we can do a shorthand notation for this. The shorthand notation recognizes that this noble gas, so these are the inert gases, these are the ones where the S and P subshells are completely filled, right? So we look at the noble gas in the row ahead of the one that we've written. And we write that iron has an argon core. So it has all the same electrons as argon. So that's what this means. All the same electrons as argon, plus then it has these 4s2 and the 3d6. So it has 3d6, 4s2. So in other words, all of these electrons up to here are the same as argon. And then the extra electrons that iron has past argon, we write out. You might be wondering how many electrons the D subshells can hold. And so if you look at the periodic table, there are 10 elements here. That means that the D subshell can hold 10 electrons. Remember that for D, L is equal to 2, which means that M sub L can be -2, -1, 0, 1, and 2, meaning that there are 1, 2, 3, 4, 5 subshells within this D subshell. There are 5 degenerate orbitals. Each of these 5 orbitals can take 2 electrons, so 2, 4, 6, 8, 10. So the D level can take 10 electrons. So this D level is not filled, right? Okay, so the next thing we need to think about is how do we write the electron configurations for ions? So for negative ions, there's not really much of an issue. Let's look at oxygen, for instance, and let's do the oxygen 2- ion. The first thing I would do would be to write the electron configuration for oxygen. So oxygen has a helium core, so I can write that as helium. And then beyond helium, it fills 2s and 1, 2, 3, 4 2p's, right? So we've got 2s, 2, 2p, 4. But I need to put 2 extra electrons in there. The p level can take up to 6, and so I am going to add 2 electrons here and make that 2p6. So now my oxygen 2- has 2 extra electrons. Those 2 extra electrons, 1, 2, make it have the same electron configuration as neon. So I could simply represent it this way as the same electron configuration as neon. When ions and atoms have the same electron configuration, these are called isoelectronic. Same electronic configuration, right? So if we look at, for instance, fluorine-, it has a helium core. It fills the 2s2, and fluorine itself has 1, 2, 3, 4, 5 electrons in the 2p, but I'm going to make it minus, so I'm going to give it one more, so I'm going to give it 6 electrons in the 2p6, and so that also has a neon configuration, and so these guys are also isoelectronic. So that's negative ions. Just add another electron to the next available orbital. That's how we get negative negative ions, anions. If we want to do cations, so positive, then we're removing an electron. Now, it's a little bit trickier to remove an electron or remove more than one electron. So let's look back at our iron, right? We had the electron configuration for iron that was argon, and then 1, 2, 3, 4, S2, 3D6, or we could write that as argon, 3D6, 4S2. So if I am going to write, let's do iron 2+ first. If I want to take 2 electrons away from iron, the trick here is that you don't take them out in the same, just the reverse order that you put them in. So you always take the electrons from the highest n level first. The highest n level first. So 4 is bigger than 3, so I'm going to take them out of the 4s orbital and leave them in the 3d. So to take 2 electrons away, I need to take them from the orbital that has the largest n number. So iron 2+ is going to be argon 3d6 because I'm going to remove both of these 4s2 because I need to remove 2 electrons to make a 2+ ion. If I wanted to make iron 3+, now I need to take one more electron away, and that's going to have to come out of the 3d level. So I take one more electron away, that the only place to take it from is the 3d level, so I take it from there. Notice that this has the same electron configuration as manganese 2+, which if you work it out is going to be argon 3d 5. And so iron 3+ and manganese 2+ are isoelectronic.